Hello students, welcome to Online Maths Classroom. In this video, we'll learn about increasing and decreasing functions and concept of tangents and normals. We'll also solve exercise 6.2. So let us start with it. Increasing and decreasing functions. In this section, what we will do, we will use the concept of differentiation to find out whether the function is increasing or decreasing or it is none. Okay, so for it we will consider a function like fx equal to x square for x belonging to R. Now this is a quadratic polynomial and you are familiar with it that the graph will be a parabola. Okay, touching x-axis at origin. It's a parabolic graph, right? You can take different points and then plot like this, but just for example, as we are already familiar with it also, that quadratic polynomial is having a parabolic graph. Now let us interpret this graph. What happens that observe that as we move from left to right along the graph, what is happening? The height of graph continuously increases. See from here at this point what the height is, okay, and to this point the height is rising above. Okay, so for this reason we say that the function is increasing for real number x greater than 0. Whereas what is happening as we move from left to right along the graph, the height of the graph continuously decreases. Okay, from left to right we are moving. Okay, from left to right we are moving. So that means I'm asking about left to right. So that means from here this height is more and here it is less. Okay, so means it is decreasing, right? So what is happening that the function is decreasing for real number x greater less than 0. Okay, now we shall give some analytical definition for it. Now let us see the definition that I be an interval contained in the domain of a real valued function f, then this f is said to be increasing on I. If for x1 less than x2 in I, f of x1 is, here it should be less than equal to. Okay, so do the correction. It is less than equal to. Okay, here it is like greater than equal to, here it should be less than equal to. For x1 less than x2 in I, f of x1 is less than equal to f of x2 for all x1 x2 belonging to I. Okay, for all x1 x2 belonging to I. That means at smaller point the value of the function should also be smaller. In that case the function is increasing on I. And in case of strictly decreasing function on I, if the definition is same, x1 x2 belongs to I, f of x1 is strictly less than f of x2. Here the sign equal to is also involved. Okay, for all x1 x2 belongs to I, and is called as a constant function on I if fx is equal to c for all x belonging to I. Means function is just having a constant value in I. Okay, and decreasing on I if for x1 less than x2 in I, f of x1 is greater than equal to f of x2. Okay, for all x1 x2 belonging to I. Means at smaller point the value of the function is greater and at larger point it is less. So in that case the function is decreasing. And strictly decreasing means for x1 less than x2 in I, f of x1 is greater than f of x2 for all x1 x2 belongs to I. Okay, so see from here, this is the graph of strictly increasing function. So as you can see, at smaller point the value is less and the greater point as it keeps on moving, so the function is attaining the greater values. And here at the larger point, see, so means say smaller point, some point 1 is here and some point say 5 is here. Okay, so at the larger point, the smaller point function is having greater value. Okay, it is having the greater value, this greater value, and at the larger point it is having the less value. So in this case the function is decreasing, and this is the case of a neither increasing nor decreasing, or we can see the graph of a constant function. It is neither increasing nor decreasing. Definition number 2 says let x not be a point in the domain of definition of a real valued function f, then f is said to be increasing, decreasing at x naught if there exists an open interval I containing x naught such that f is increasing, decreasing respectively in I. Means a function is said to be increasing or decreasing in an at a point x naught if some open interval is existing in which this point x naught is lying, okay, such that the function is increasing or decreasing respectively in this interval I. So let us take an example like show that the function fx equal to 7x minus 3 is increasing on R. R means set of real numbers. So what I will do, I will take 2 points, let x1, x2 belongs to R and x1 is less than x2 such that, so I'll try to make this function. So like 7x1 is less than 7x2 and 7x, if I'll subtract the same number, the result will be same. Okay, 7x1 minus 3 is less than 7x2 minus 3. That means f of x1 is less than f of x2. So that means the condition is that x1 less than x2, f of x1 is also less than f of x2. So by definition 1, it says as the strict sign is there, so it is strictly increasing on R. Okay. Now there is a theorem that let f is a continuous function on AB, as we have studied everything like this in our Rolle's theorem and mean value theorem, that f is a function continuous on closed interval AB and is differentiable in open interval AB, then this function is increasing on AB if f dash x is positive. Okay, increasing. See, you were familiar with in case of how we do that. See, this is the curve. So rate of change is positive, derivative is positive. Okay, so up to here what is happening to the function? It is increasing. Why? Because my derivative f dash x, that is turning out to be greater than 0. Okay, and see from here in this interval towards this side what is happening? The derivative is decreasing. That means my f dash x is turning out to be less than 0. Okay, so it is decreasing. And if it is constant, then what will happen? Like this from here, like we have studied in Rolle's theorem also, the value of the derivative is 0 for each x belonging to AB, means no change, neither it is positive nor it is negative. Okay, so you need to prove this theorem. So what we can do is we can use the mean value theorem. Okay, that we know according to it that if a function is continuous in AB, differentiable in open interval AB, then by mean value theorem there exists a point C between these 2 points x1, x2 such that f of x2 minus f of x1 equal to f dash C upon x2 minus x1. You know that that slope at that point means f dash C was equal to f of b minus f of a upon b minus a. So on cross multiplying we will get this condition. Okay, now as my this derivative is positive, right, as f dash C is positive, it is given. Okay, and my this x2 minus x1 is again as the larger point, it is again positive. So this side is positive, that means f of x2 minus f of x1 is greater than 0. Okay, so f of x2 is greater than f of x1. Therefore, when we'll have x1 less than x2, what is happening? That this f of x1 is your less than f of x2 for all x1, x2 belonging to AB. Okay, so what happens? This is the condition for increasing function, as we have done earlier in our theorem. What is happening? That my f of x1 for x1 less than x2, my f of x1 is also turning less than f of x2 for all x1, x2 belonging to AB. That means my function is increasing function in AB. Okay, so the second part can also be proved as for that condition the derivative will be negative. Okay, and the third condition can also be proved. Now let us start with exercise. Number 1 is show that the function given by fx equal to 3x plus 17 is strictly increasing on R. So this is a simple question. I'll just take the derivative. Okay, the derivative is turning out to be 3, which is positive for all real numbers. So that means the function is strictly increasing on R. Second is fx equal to e raised to power 2x. So when I'll differentiate it, I'll get it as 2e raised to power 2x, which is always positive for all real numbers. Why? Because e is a number which is approximately equal to 2.718, right, which is always positive. And even if I raise it to power negative, see like this, a quote is here that e raised to power minus 2, it will also become 1 upon e square like positive. And even in case of zero real number, e raised to power 0 is 1, which is also positive. So I can conclude that this derivative is also always going to be positive. That's why my function is strictly increasing. Number 3 is show that the function defined by fx equal to sin x is strictly increasing on 0, 90, decreasing on pi by 2 to pi, and neither increasing nor decreasing on 0, pi. So this is my function sin x, derivative is cos x. Okay. Now my derivative, see my derivative, it is positive. Positive in which quadrant? First quadrant. That is my 0 to 90. So I say this is strictly increasing in 0 to 90. It is strictly increasing in 0 to 90. Okay. Now B is, we know that my derivative is cos x, which is negative in quadrant number 2. That is pi by 2 to pi. So that means my function is strictly decreasing on 90 and pi. Now what is happening? That my function, derivative of the function, is positive in 0 to 90, negative in my quadrant number 2, that is pi by 2 to pi, and moreover the value of the derivative at pi by 2 is 0. So what is happening, that f dash x does not keep the same sign in the complete interval 0 pi. So that means we conclude that it is neither increasing nor decreasing in 0 and pi. Okay. Number 4 is, my function is this 2x square minus 3x is, I have to prove that find those intervals. I have to find the intervals here in which the function is strictly increasing and decreasing. Okay. So how will I go? This is my function. This is my derivative. Okay. Next step is to find the critical point or turning point. That will I find by putting derivative equal to 0. So when I'll put my derivative equal to 0, that is 4x minus 3 equal to 0 will give me x as 3 by 4. So I can convert it to decimal, or otherwise I can avoid it also. So that means 1 point means 2 intervals. One is starting from minus infinity to infinity, and in between the turning points. Okay. Always 1 is 1 and 2 is 2, then they are 2. So if 1 point is there, 2 intervals will be there. So like they are from minus infinity to 3 by 4 and 3 by 4 to infinity. Now let us check my derivative sign. This is my derivative, and minus infinity to 3 by 4, I'll take 1 point, say 0 0.5. So see, if I put 0 0.5 here, this derivative is turning out to be negative. That means my function is strictly decreasing. And 3 by 4 to infinity, let's take 1. So my derivative, say if I put 1, the derivative is positive. Means my function is strictly increasing. So this is how I check. That means my function is strictly increasing in 3 by 4 to infinity and decreasing in from minus infinity to 3 by 4. Okay. Next is find the intervals in which the function given by fx equal to 2x cube minus 3x square minus 36x plus 7 is strictly increasing and strictly decreasing. So start with the function, take the derivative, frame the factors. Okay. So that I can just check. I will not omit this 6. Okay. This is to be retained here. And I'll make factors. So it is 6 times x plus 2 into x minus 3. Now put derivative to 0 to get the turning or critical point. So 6 is not equal to 0. That means x plus 2 is 0. X minus 3 is 0. I get 2 critical points, minus 2 and 3. So breaking will be in 3 intervals, 1, 2 and 3. One is from minus infinity to minus 2. Second is minus 2 to 3, and other is 3 to infinity. And now I'll check my derivative in between all these points. So from minus infinity to minus 2, I can take minus 3. Okay. Don't keep it in mind that minus 1 I can put. Okay. Because sometimes we say that, okay, minus infinity and minus 2, minus 1 is lying. That is wrong. Minus 1 is not lying in between. Minus 3 is lying. Okay. So put minus 3. I'll get it as positive. This is as negative. Okay. This is as negative. So overall result is positive. My function is strictly increasing in this interval. And between minus 2, 3, I can take 2. And here the function is positive, negative, and my function is strictly decreasing. Okay. And from 3 to infinity, say 0.4 is there. The overall result is positive and function is strictly increasing. Okay. So my function is strictly increasing in minus infinity to minus 2 and 3 infinity. I can put a sign of union here also. That means this function is strictly increasing in this interval and decreasing it is in minus 2, 3. Okay. Number 6 is find the intervals in which the following functions are strictly increasing or decreasing. So let us do one by one quickly. So this is my function. The derivative is 2 times this x plus 1. To find critical point, put it is equal to 0. And I'll get my turning point as minus 1. Okay. So 2 intervals will be there, minus infinity to minus 1 and minus 1 to infinity. So let us take a point here to check the derivative. Say it is minus 2, it turns out to be negative and it is decreasing. And between minus 1 to infinity, I'll take x 0, which is positive. So function is strictly increasing. So I got that it is increasing in interval my -1 to infinity and decreasing in -infinity to -1. For B part, this is my function, the derivative out there. Okay, the critical point is -3/2. Again, two intervals, -infinity to -3/2, -3/2 to infinity. Okay, so here I'll take a point -2. This is my derivative behaving positive, function strictly increasing. In this, I'll take x as -1. It is less than 0. Function is strictly decreasing. Okay. For C part, this is my function. The derivative after factorization, it is -6 times x plus 1 into x plus 2. So critical point will give me x as -1 and -2. So how many intervals? 3. -infinity to -2, then -2 to -1, and then -1 to infinity. Now let us check the derivative. So between -infinity to -2, take a point -3. The derivative turns out to be negative. So that means function is strictly decreasing. Between -2 to -1, I'll take point -1.5. Here the function is derivative is turning out to be positive. So function is strictly increasing. And in -1 to infinity, you can put x 0 and the value of the derivative is negative. So function is strictly decreasing. Okay. So what can I conclude it? Function is strictly increasing in -2 to -1 and decreasing in these two intervals. So these two intervals can also be joined by putting the sign of union here. Okay. Now let us see question number D. Fx is your 6 minus 9x minus x square. So this is my derivative. Okay. So there is also one other way, as it's a simple question. So function is strictly increasing if my derivative is positive. So see my derivative, 9 minus 2x is greater than 0. Okay. So that means minus 2x, take it to other side, is greater than 9. That means x is less than -9/2. Okay. I have to multiply with negative sign to make x positive. And this will change the direction of inequality. So that means x is -9/2. So that means my interval is, as I know that the critical point will be 9/2, then only there will be two intervals, like one is -infinity to -9/2, another is -9/2 to infinity. So function is strictly increasing in this. Okay. And similarly for the other case, if this is derivative is negative, so my x is greater than -9/2. So function is going to be strictly decreasing in this interval. E part is, this is my function. Okay, so this is my derivative. I have to use the product rule here, and here I come after reduction to the proper factors form. Now as I see that these both x plus 1 whole square and x minus 3 whole square, they are all positive. So the positive and negative nature only depends upon this x minus 1. Okay, so my function will be strictly increasing if my derivative is positive. That is, this 6 is always positive, other 3 are positive. So x minus 1 should be greater than 0. That is, x is greater than 1. And will be decreasing if this is less than 1. Okay. So that means my function is strictly increasing in interval 1 to infinity and decreasing in -infinity to 1. Okay. Number 7 is, show that function y is equal to log 1 plus cos x minus 2x upon 2 plus x. This is with x greater than -1 is increasing function throughout the domain. Okay. So for looking at it, let's differentiate the function first. So this is your 1 upon 1 plus x, and ddx of 1 plus x is 1, and it should be differentiated using quotient rule. Okay, be careful with the sign outside here. So after reducing, we reach here, and then I have to take the LCM. So after taking LCM, I'll come up here. Okay, so you can see x square is always positive, 2 plus x whole square is always positive, and x should not be equal to -1, as if it is -1, then my function will be reducing to infinity, undefined form. Okay, so here the domain of the function gives x greater than -1. Okay, so lot many factors are there, that as log is not defined for the negative terms, or I have to keep this function be there, that the derivative is also existing. So that condition is fully satisfied. Okay, so to be the function to be increasing function, what condition should be there? That this x plus 1 should be positive. Okay, as other are always positive. So that means my x is greater than -1. Okay, so function will be your increasing function, where x is greater than -1 condition is already given. Okay, as we know, for increasing function, the value of the derivative should be greater than equal to 0, and for increasing, strictly increasing function, it should be strict greater than 0, and for increasing it should be greater than equal to. Similarly, for decreasing it should be less than equal to 0, and for strictly decreasing it must be, strict sign should be there. Number 8 is for values of x you have to find for which this function is increasing. So let us start with the derivative. So my derivative turns out to be, after proper factorization, it turns out to be 4x, x minus 2, x minus 1. So let's check the critical points. As 4 never equal to 0, so x is 0. From here x is 2, x is 1. So 3 points means 4 intervals. One is minus infinity to 0, this one, then 0 to 1, then 1 to 2, and then 2 to infinity. Okay. So let us check my derivative. This tabular form is much convenient and is much simpler. So from minus infinity to 0, take a point x as -1. So this turns out to be like 4 is positive, this is negative, this is negative. Okay. So this is negative. So overall result is less than equal to 0. Okay. So what I see, that function is decreasing. And at from 0 to 1, take 1 by 2. So this is positive. So function is increasing. For 1 to 2, take 1.5. So it is turning out to be, your result is turning out to be negative. Okay. Negative, or I say less than equal to 0. So that means my function is decreasing. Okay. And for 2 to infinity, take 0.3. So I'll check, as if I put 3, it is positive, positive, positive. So it is greater than equal to 0. Okay. So function is increasing. So I must say that the function is increasing in the interval 0, 1. Okay. This my function is increasing in the interval this 0, 1 and 2 infinity. Okay. So I can put a sign of union also. Question number 9 is, prove that y is equal to 4 sine theta upon 2 plus cos theta minus theta is an increasing function of theta in the interval 0 to pi by 2. Okay. So let us start with its derivative. So I have to differentiate it with respect to theta. Like dy by d theta will be, I have to apply the quotient rule here, and dd theta of minus theta will be -1. So this is quotient rule applied, and then thereafter I have to make it one function and take LCM thereafter. So see, after this step, 2 plus cos theta whole square taken here, and then after opening, this 4 times cos square theta plus sin square theta changes to 1, and the opening of this 2 plus cos theta whole square bracket will give me this result, 4 cos theta minus cos square theta in the numerator, from which I can take cos theta common, and it becomes 4 minus cos theta upon the denominator is 2 plus cos theta whole square. Now, since you know that in first quadrant, okay, the value of cos is lying between 0 and 1, and moreover we also know that cos is having its value between -1 and 1. Okay, but 0 and 90, the value is lying between 0 and 1. Therefore, say the 4 minus cos theta term will always be positive. Okay, right, and the denominator is altogether positive everywhere because it is a whole square. So everything depends upon this cos theta. Okay, this cos theta. Now my dy by d theta is positive, as you know that for theta lying in first quadrant, cos theta is positive. So that means this y is an increasing function in 0 to pi by 2. Number 10 is proof that logarithmic function is strictly increasing on 0 infinity. Now the function is log x, derivative is 1 by x, which exists only for x greater than 0. Okay, for all x belonging to 0 to infinity. Okay, because x is positive. So you know that this function, as for x0, it is not defined. So be careful about this open bracket towards this side. So this function is strictly increasing on 0 to infinity. Okay. Now prove that the function f given by fx is equal to x square minus x plus 1 is neither strictly increasing nor strictly decreasing in -1, 1. So remember that example in which you know that neither strictly increasing decreasing means if throughout the interval the behavior is not same, means either it is not increasing but it is mixed, halfway it is increasing, halfway it is decreasing. In such cases the functions are said to be neither increasing nor decreasing. Okay, so let us see, this is my function, this is the derivative. So the critical point is my, putting 2x minus 1 equals 0, I get my function critical point as half. So 2 breaking of the intervals will be there, that is my -1 to half and half to 1. So either you can go for the tabular method, or you can go like this also, as we say that function is strictly increasing if f dash x is positive, that is 2x minus 1 is positive, that is your x is greater than half. Okay, and will be strictly decreasing if this derivative is less than 0, that is 2x minus 1 less than 0, that is x is less than half. Okay, so that means as I have not go for minus infinity and infinity, as my boundaries are defined, I have to see the behavior of the function in minus 1 and 1. So for x greater than half means the interval I'm talking about half to 1. Okay, and for strictly decreasing means I have to take the interval from minus 1 to half instead of minus infinity to half. So this is clear that function as it is halfway it is increasing, halfway it is decreasing. So it is neither increasing nor decreasing, neither strictly increasing nor strictly decreasing on the complete interval minus 1 to. Next is number 12. Which of the following functions are strictly decreasing on 0 to 90? This is the first quadrant. So let us see cos x, then we will see later on these all functions. Now fx is in your function given here is cos x. I'm taking part A, derivative is minus sin x, and we are talking about the first quadrant. X is lying in first quadrant, and you know where I have to see actually the derivative part. So sin x is positive in this quadrant, but minus sin x will be negative. Okay, so that means function is strictly decreasing on 0 to 90. Now for cos 2x, the derivative is minus 2 sin 2x. Now remember here, the interval is for 0 to 90. If I have to take here as 2x, so I have to multiply the interval, and now this question shifts to first and second quadrant both. First and second quadrant both. Add from 0 to 180 now we are talking about. And in both these quadrants, sine of anything is positive. Sine theta is positive in first and second quadrant, and therefore minus sine 2x will be negative. So my derivative is negative in this quadrant, so function is strictly decreasing on 0 to 90. Okay, we have not to see the function, we have to see the derivative. Now come to cos 3x. Now this is cos 3x, this is the derivative. Okay, now again as the derivative, this interval is for x, so for 3x I have to multiply by 3. So this is 270 degree. Now remember that between this interval the function is you have to see, as I have to see sine even. Okay, so in this case both first, second, and even the third quadrant are also included. So we have studied about the behavior of my sine, that in quadrant number 1 and 2 it is positive and minus of it will be negative, right? So see, as we're talking about say for this 0 to 270 degree, we say that this 3x between first two quadrants, like from 0 to pi, will be positive, okay, in the first two quadrants, right? But derivative, as it is minus sine 3x, so it is negative. So function is strictly decreasing in 0 to pi by 3. Okay, 0 to pi by 3. As my interval for 3x is 0 to pi, then for x it will be from 0 to pi by 3. Okay, and for the next means from pi to 3 pi by 2. Okay, the next interval. This sign is negative, as it is negative in the third quadrant, but minus sine 3x will be positive. So my function is strictly increasing in pi by 3 to pi by 2. See from here, I will make this quadrant for x. So x will be, I should get divided by 3. So it becomes from pi by 3 to pi by 2. Okay, so my function is neither strictly increasing nor strictly decreasing on 0 to pi by 2. So halfway the behavior is different, halfway the behavior is different. So it is neither strictly increasing nor strictly decreasing. Now go for tan x. Tan x derivative is secant square x, which is always positive. Okay, and moreover in your first quadrant, as x is only there, so in first quadrant all are positive and secant square is always positive. So the function is, this is also strictly increasing. So only my option number A and option number B are strictly decreasing functions. Question number 13 is, on which of the following intervals is the function given by fx equal to x raised to power 100 plus sin x minus 1 is strictly decreasing? So these are my intervals 1, 2, 3. Okay, so let us see. So this is my function and the derivative is 100x raised to power 99 plus cos x. So let us test for the option number 0, 1. Okay, so in 0, 1 my x is positive, that means 100x raised to power 99, this is positive. Okay, and cos x in interval 0, 1 means 0, 1 is the radian measure here, so which turns out to be 0 to 57 degree nearly. So you can calculate it, here the calculation is done. So there is no need to do it in examination, it's just for understanding purpose. So what do I turn out? That my derivative is complete, as this term is positive, this term is positive, so it is strictly increasing on 0, 1. Okay, so means option number 1 is not the correct option. Okay, A is not the correct option. So go for option number B, from pi by 2 to pi. So see, from pi by 2 to pi, I can put the values of pi as 22 by 7. So I check it as the values is this, right? And for x greater than 1, x raised to power 99 is positive, as therefore 100x 99 is greater than 100. And for the second interval, second quadrant, I will see cos x is negative, because it has the value between -1 and 0. So in total, what happens is that this value is 100 minus 1, which is 99. So overall result is positive. So my function is strictly increasing on pi by 2 to pi. So that means my option number B is also not the correct option. So let us go for 0 to 90, as it is 1.5, by changing it to 22 by 7. So 100x raised to power 99 and cos x both are positive. So this is also positive. So strictly increasing in 0 to pi by 2 also. So that means it is also not the correct option, because in first quadrant it is very clear that how cos is behaving, and the values we can place to check whether how my rest is 100x raised to power 99 and cos x are behaving. So here also it is not decreasing. So means D is the correct option. Question number 14 is, find the least value of A for which my function fx equal to x square plus ax plus 1 is strictly increasing on 1, 2. So this is my function, this is the derivative. So as it is strictly increasing on 1, 2, that means my derivative 2x plus a should be positive for all x in 1, 2. Right? Now on 1, 2, x is lying between 1 and 2. I will make it as 2x plus a. So firstly I'll multiply with 2 throughout. So it becomes 2x lying between 2 and 4. And adding a, it will become 2 plus a. Okay, less than 2x plus a, less than 4 a plus e for all x in 1, 2, right? And this is my derivative, so f dash x lying between 2 plus a and 4 plus a, right? So minimum value is 2 plus a and maximum one is 4 plus a, right? But I know that my derivative should be positive for increasing function, strictly increasing function. That means both these values should be positive. Okay, that is a is greater than -2, a is greater than -4. So a is greater than -2. Why? Because if a is greater than -2, automatically a greater than -4 is automatically there, right? See from here, this is my 0. So see, some -2 is there. Okay, and see here the value -4 is there. So whatever is greater than -2 is automatically greater than -4. But whatever is greater than my -4, okay, means -4, maybe the value is lying here. So means it is not satisfying for -2, right? So a is greater than -2, we will consider. Okay, and the least value is, no doubt the sign here is of greater than. So the least value, if I take it, is -2. Okay, not more than it. I have to, as it is strictly my increasing function, so I have to consider my least value as -2. Number 15 is, I is an interval disjoint from -1 to 1. Prove that this function x plus 1 upon x is strictly increasing on I. So this is my function. To avoid the quotient rule, I will write it as x plus x raised to power -1, and on derivative it is 1 minus 1 upon x square. So on factorization it becomes a plus b into a minus b upon x square, right? So when I take the critical points, two critical point -1 and 1 are there. So 3 intervals will be there like this. Okay. So I'll take the intervals as, say, -infinity to -1, -1 to 1, and 1 to infinity. So let us check my derivative for x less than -1, say x minus 2 I'll take. So if I'll put -2 here, it is negative, and denominator is positive. So overall result is positive, right? And for x greater than 1, say I take 2. So it is positive, positive, and positive. So overall result is positive, right? So f dash x is 0 for all x belonging to I. That means my function is strictly increasing on this interval I. Okay, right? Strictly increasing on I. Okay, disjoint from this means I have to check only an interval disjoint from this, means leaving behind -1 and 1. So if you will check the behavior between -1 and 1, you will find that the function is showing the reverse behavior, that is, it is turning out to be decreasing. But in both these intervals, the function is giving you strictly increasing behavior. Number 16 is proof that the function given by fx equal to log sin x is strictly increasing in 0, 90 and decreasing in 90 to pi. So this is my function, derivative is 1 upon sin x and derivative of sin is cos, so it is cot x. Now interval 0 to 90 in first quadrant, cot x is positive. So function is strictly increasing, right? So I'm checking my derivative is turning out to be positive, which is cot x. So function is strictly increasing in 0 to 90. And on the second quadrant, you see that my derivative is negative, less than 0. So it is strictly decreasing in pi by 2 to pi. Similarly, for my log cos x is decreasing in 0 to 90 and increasing on pi by 2 to pi. So see why it is happening, as it is log cos x, so derivative is 1 upon cos into minus sign, as derivative of cos is minus sign, so it is minus tan x. Okay, now what is happening in 0 to 90 means the first quadrant, you know, tan itself shows the positive behavior, but minus tan x will be negative. So that's why the function is strictly decreasing in 0 to 90. And here in second quadrant, no doubt tan is negative, but minus tan will be positive. So my function is strictly increasing on 90 to 180, second quadrant. Number 18 is proof that the function given by fx equal to x cube minus 3x square plus 3x minus 100 is increasing on r. So we will check the derivative. It is 3 times x square minus 6x plus 3. Take 3 common and it is a perfect square, like 3 times x minus 1 whole square greater than equal to 0. So see, as I have to do the question for on r, so means it's a 1 mark question. So simply I can interpret it from here that my derivative is always going to behave as greater than equal to 0. Okay, no need to put strict sign as it is greater than equal to 0, as I will, when I'll put 1 it will be 0 also. Okay, and 3 is always positive. So that means my function is strictly increasing for all real numbers. The interval in which y is equal to x square e raised to power minus x is increasing. So for it, this is my function. Okay, and the derivative is, I have to use the product rule, and my derivative will be like this when I express it in form. So it will be x times 2 minus x upon e raised to power x. Okay, so what will happen, that when I find the critical point, I'll get the intervals as my x is, if I'll put x as 0, so there is no problem, because you know that anything raised to power 0 is 1. So now I should check my derivative is when my derivative is positive. So you can check throughout all these intervals that when my, instead if you don't want to go for the critical point also, so you can check out of these intervals in which interval my derivative is behaving as positive, right? So we find that the option 0 2, here my derivative is positive. So my function is behaving strictly increasing and interval 0 2 is the correct option. Okay, so what happens that if I want to go for the subjective, means it is, this question is not asked like an MCQ and it is, you have to go for, so you can go for the critical point. They will be like x equal to 0, x is equal to 2. Okay, right? And x equal to 0, x equal to 2. So I'll break it in intervals minus infinity to infinity, right? And here the points 0 2 will be there. So I'll break it in 3 intervals and I can check my derivatives there. So I will come to the conclusion that in this interval 0 2, my function will be behaving strictly increasing and otherwise it is strictly decreasing. Okay, right? And there is one remark also here to be mentioned, that increasing decreasing function means, or monotonically increasing or monotonically decreasing function, it have the same meaning. Monotonically means, monotone means the same behavior, means throughout. Mono means the single behavior is there. It is behaving either, if it is increasing, it is increasing throughout, and if it is decreasing, it is decreasing throughout. So this is the meaning of mono behavior. Monotonically increasing or decreasing means it is only either it is increasing or it is decreasing. Example number 13 is find the intervals in which the function given by fx equal to sin x plus cos x between the interval 0 to 2 pi is increasing or decreasing. So this is an example from an NCERT. This is my function, derivative is cos x minus sin x. So when I'll go for the critical point, put f dash x equal to 0 and I'll get tan x as 1. So I have to check all the critical point lying between 0 and 2 pi. So they will be pi by 4 and 5 pi by 4. Okay. So the 3 intervals will be there from like this, 0 to pi by 4, pi by 4 to pi by 4 and 5 pi by 4 to my 2 pi. So I have to check the derivative, that I will find that derivative is positive during this interval, right? And my f is increasing in this interval and decreasing in this interval. Okay, So I can go for checking my sign of this function, like in 0 to pi by 4 you can frame the table as you can go for it my derivative, like it is behaving like in this, as it is in first quadrant where cos and sine are both positive. Okay, and even you can put the values also here, like say I'm taking some value as 30 degrees, so my cos 30 is root 3 by 2 minus sin x is 1 by 2, which is positive value, so it is increasing. And between pi by 4 to 5 pi by 4, I'll check this value, it turns out to be negative, means function is decreasing. And between 5 pi by 4 and 2 pi, this function is positive, so again it is increasing, right? So this is how I have to make this table also. Okay, right, this is not to, you cannot write like this, as you have to check the derivative there. Okay, fill the value and then you can go for checking the increasing and decreasing nature. Now, tangents and normals are discussed in your previous part of application of derivatives. Okay, so let us see the concept of tangents and normals here. Now, what is the tangent and normal? We will use here the process of differentiation to find the equation of tangent line and normal line to the curve at a given point. Right? Now you know that equation of straight line passing through the point x0, y0 and having slope m was given by y minus y0 equal to m times x minus x0. In class 11th in straight lines you have done this. And the slope of tangent to the curve y equal to fx at point x0, y0, it is given by the value of derivative dy by dx at x0, y0. Okay, and the equation of tangent can be obtained as y minus y0 equal to f dash x0, means the slope of tangent at that point times x minus x0. Okay, so see what is the connection between tangent and normal. You know, if it is a curve, then tangent is a line touching to this curve at a single unit point. This is the tangent line, and whatever is perpendicular to this tangent at this point is called the normal line at point E. Okay, so since normal is perpendicular to the tangent, then the slope of normal is going to be negative reciprocal of slope of tangent. Okay, provided this slope is not equal to 0. So equation of normal can be carried out as like y minus y0. So here the same thing is there, y minus y0 equal to m times x minus x0. Instead I'll use slope here of slope of normal, which I can calculate. That firstly I'll calculate the slope of tangent, and then the negative reciprocal will give me the slope of normal. Okay, now if the tangent line to the curve y equal to fx makes an angle theta with the x-axis in positive direction, then you know that the slope of tangent will be tan theta, right? And the particular cases are if slope of tangent line is 0, right? If tan theta is 0, so that means theta is also 0, which means what is happening? The tangent line is parallel to x-axis, as we know that the slope of x-axis is also a 0. Okay, so in this case the equation of tangent is going to be y equal to y0, like y minus y0 equal to m times x minus x0. So as my slope is 0, so it will make all the terms on the other side 0. So y minus y0 equal to 0 will give me y equal to y0. And if theta is 90, that means tan theta is infinity, which means the tangent line is perpendicular to the x-axis, or we can say the parallel to y-axis. And in this case equation of tangent will be like my equation is y minus y0 equal to say m times x minus x. So what is happening now here? It is infinity, so I can take it to other side. So 1 upon m will become 1 upon infinity is 0. So this side will completely become 0 when I'll shift this m to this side as 1 upon m. Okay, and I'll remove it from here. So x minus x0 will be equal to 0. So that means x is equal to x0. Okay, so more questions of depending upon this your and normals will do in our previous part. Okay, they are done in our previous part number 4. Okay, so check out for the solutions there, right? And I hope the concept of increasing and decreasing functions is clear to you. Practice it well. It's a very important concept and is simple also. Thank you so much.